Welcome to module 15 of the course Ultrafast Optics and Spectroscopy. Here, one question remains open. We said that nuclei will move in a system. Now, question is why nuclei should move in a system. Atoms move due to Hellman-Feynman force acting on them. The force, which is nothing but negative of the potential gradient, and the potential is nothing but is represented by this expectation value of the electronic Hamiltonian, and if we plug that in, then what we get, we can get an expression for F, and that is nothing but minus partial derivative with respect to R, this psi electronic R Hamiltonian, electronic Hamiltonian, psi electronic R integration over the electronic coordinate. So if we take this first derivative, that's the force, then we can write as follows: minus psi electronic R, this is parametric dependence, then the first derivative of the Hamiltonian, then psi electronic R, this is one derivative. Second derivative is going to be second term is going to be the first derivative of the wave function, which is R. So we'll consider this force acting on a particular nuclei. So let's say I have a system with n number of nuclei. We are talking about this nuclei denoted as I. That's why we are talking about I coordinate. So with respect to I coordinate, we are going to take a look at this problem. This is going to be I coordinate. So with respect to ith nuclei, we get the first derivative, electronic R, electronic Hamiltonian, psi electronic R minus psi electronic R electronic Hamiltonian this is the way we get three terms, and we can simplify these terms, particularly last two terms. We can simplify these two terms. We can simplify as follows. We can rewrite these two terms as electronic expectation value. This is electronic energy with respect to ddr I psi electronic R, and what we see that this integral, so this derivative can be rewritten as follows, and we can make this derivative to be 0 because orthonormal, we have taken orthonormal set for the electronic wave function, and if it is orthonormal, then if they are the same electronic state, it is going to be 1 or 0. So this integral, it takes either 0 or 1 value, and that's why the first derivative is going to be 0. So this term will be 0. Finally, what we get is that we get this force acting on ith nucleus is going to be, can be calculated as psi electronic wave function r r, the first derivative with respect to r, psi electronic r r. So this is the expression for the Hellman-Feynman force, and because of that force, nuclei will always move, and the ultimate motivation in molecular dynamics to reduce this force in a system. At equilibrium, when this is the potential energy V, or we can write down V electronic energy, anything is right, V or V electronic energy. So we said that electronic energy can be calculated as a for different R. R behaves like a parameter here, and we get the potential energy curve or potential energy surface. In the potential energy surface, at the equilibrium point where the force at this point we know that the first derivative, that is dV dr, is going to be 0. That is why force is 0. So this point is called equilibrium point. So at equilibrium, Fi on the ith nuclei, for the particular nuclei, this force is going to be 0, and out of equilibrium, this force is not going to be 0. So for example, when we excite a molecule to the electronically excited state, it reaches a potential energy surface which is entirely different from the ground state potential energy surface, and at this point we had force was 0 because the gradient of the potential gradient was 0. But at this point, potential gradient is not necessary to be 0, and in that case we get F on acting on the ith nuclei is not going to be 0, and that can be calculated from the potential gradient at that point. So in mixed quantum classical picture, one can then write that F I, force acting on ith nucleus, is going to be mi, that is the mass of the nucleus, and the acceleration acting on the ith nucleus. This can be calculated from this expression, electronic wave function r r, the first derivative of electronic r I, psi electronic wave function r r r. So this is the expression we can get. Therefore, when photoexcitation prepares system out of equilibrium, ultrafast molecular dynamics can predict physical movement of atoms for a fixed period of time after photoexcitation. Why molecule should move on the upper electronically excited state? So this is your excited state, this is your ground state, and on the excited state it should move just because the force acting on it is not 0. It has certain force, and because of that force, nuclei will move. Force can be calculated from the derivative of the potential energy curve at that point. So in this figure, we are showing that at a point A, this point is considered to be A, let's say. At point A, atoms of the system will not move. But at point B, if we call this point to be B, at this point atoms should move because the system is out of equilibrium. Here we note that mixed quantum classical approach is not the only way to deal with ultrafast quantum molecular dynamics. Pure classical and pure quantum mechanical methods are also available. In a pure classical method, no well-defined nuclear wave function is used, and in pure quantum mechanical method, well-defined nuclear wave function, which is vibrational wave function, is used. We shall, however, stay focused on the mixed quantum classical approach because this approach is easy to grasp for the beginners. So, what is the basic idea in ab initio molecular dynamics, particularly following mixed quantum classical approach, is that nuclei will move only when there is an force acting on them, and force can be calculated directly from potential gradient. Potential can be calculated from electronic structure theory calculation. So, I have a system having n number of nuclei, this is n, and this system will evolve, which means that position and momentum of different nuclei will change because force acting on them is not zero. And how do I get that force? Force can be calculated from the potential gradient, and this potential gradient can be calculated from electronic structure theory calculations, because I need, from electronic structure theory, I need this expression, the electronic wave function I need. So, basically what I get is that from Hellman-Feynman theorem, we get that this electronic wave function we get from electronic structure theory calculation psi electronic. So from this, this wave function we obtain from electronic structure theory calculation. From this wave function we get this force acting on it, and once we know the force, then using Hamilton equations we can get next position and momentum after delta t time, and delta t is taken to be very short time. So, nuclei will move following classical equation of motion, but it will move on a potential energy surface depicted or provided by the electronic structure theory calculation. That is called mixed quantum classical methodology. Majority of the ab initio molecular dynamics simulations described in the literature assumes that Newtonian dynamics is sufficient for nuclei, and electronic Schrodinger equation provides the potential energy surface. This approach is called mixed quantum classical approach and emphasizes the close relationship between the electrons that govern the form of the potential energy surface and the nuclear dynamics that occurs on this potential energy surface. The mixed quantum classical approach to ab initio molecular dynamics is well justified by the fact that electrons are lighter than nuclei. This is why, to a good approximation, electron will rearrange quickly when nuclei move. However, the quantum mechanical nature of the nuclei becomes crucial for even a qualitative understanding of many chemical problems. For an example, tunneling. An important chemical problem in which nuclei should be described quantum mechanically is when the Born-Oppenheimer approximation breaks down, as is always the case in photophysics and photochemistry involving conical intersection. In particular, we will go over ab initio multiple spawning, which explores molecular dynamics through the conical intersections. Ames method, ab initio multiple spawning method, is a mixed quantum classical approach but treats both electrons and nuclei quantum mechanically. We will discuss this method, ab initio multiple spawning method, keeping photophysics and photochemistry in mind. In any quantum molecular dynamics, we begin with time dependent Schrodinger equation. Time dependent Schrodinger equation reads as follows: I, the derivative with respect to t, the total wave function derivative of the total wave function is equal to the Hamiltonian and the total wave function. Here atomic unit is used. In atomic unit we consider H reduced Planck constant to be 1. Now, for this time dependent Schrodinger equation, the first point we have to clarify is that what would be the trial solution for this. And in general, either Born expression or Born-Oppenheimer expression so there are two approaches we follow to express the trial solution, trial wave function. Either we use Born expansion, what does it mean, we'll show very soon, and or we use Born-Oppenheimer expression for the total wave function. In both expressions, however, we use the product of electronic wave function and nuclear wave function. That is quite common, but the expressions are slightly different depending on what kind of expression we use. Let us first understand the electronic wave function. When electronically ground and excited states are well separated in energy, for an example, the situation depicted here, we show that the ground state potential energy surface is well separated from the excited state potential energy surface. Let's say this is your S1 excited state, this is your S0 ground state, and they are well separated. Let's say they are separated by 5 eV energy difference. So if they are well separated, then one can easily assume that the total electronic wave function, and if we say that system is in the ground state, then one can easily assume that total electronic wave function adopts mostly single electronic configuration. To understand this, we can take an example of ethylene. Let's say ethylene molecule we have ethylene molecule, and in the ethylene molecule we have sigma bond, then we have pi, then we have pi star. These are the orbital alignments, let's say. And pi was W occupied, sigma W occupied, and then pi star is not W occupied, it is empty. And then we had sigma star as well, like this, empty orbitals. So when we say electronic configuration, we mean this configuration, how we write down or fill the orbitals, molecular orbitals. So we'll say that if it is in the ground state, if the ethylene in the ground state, then we can write down the configuration as lower energy orbitals are shown in these dots. We are not writing explicitly, we are just writing the valence orbitals, high lying energy orbitals. So sigma 2, we have 2 electrons occupied in the sigma orbital, then pi 2, and then pi star is going to be 0. So this is going to be, and then sigma star is also 0, and few dots because we have many other antibonding orbitals as well. So this configuration, we'll call it a ground state electronic configuration. And ground state electronic configuration and then excited state configuration, one can think of again dots, then sigma 2. One electron from pi can be excited to the pi star, and sigma star is 10 0. This is going to be, let's say, one of the excited state electronic configuration. So this is the only difference in the excited state configuration, where we have excited. So this is your ground state configuration. Then for the excited state configuration, we'll write down in a similar fashion. We have this pi star, then sigma star, and then pi, and then sigma here. These are W, this is W occupied, this is now singly occupied, this is now singly occupied, and then we'll call it S. So basically we should have electrons like this, because this is a singlet excited state, and we can say that this is excited state configuration. So this way one can think of creating many configurations, and we'll say that, okay, if the system is in the ground state, we will assume that mostly the total electronic wave function component can be expressed by this. And in other words, pictorially here, what we have is that there are balls we have shown. So this big ball is presented by the configuration this. Then this green ball is representing configuration this. And we can say that the contribution of total wave function, this high electronic wave function, can be written as mostly this red ball. We will not have much contribution from the upper electronically excited states because their separations are long. They have excited states and ground state separation is very, very large. Now, if we consider the ground electronic state of ethylene, to a good approximation, one can accept that ethylene ground state electronic wave function can be represented by the only big ball, and that's exactly what we are trying to show. And big ball is a particular configuration, ground state configuration. And in that case, total wave function can be represented approximately like this. I have nuclear. I said that in either Born expansion or Born-Oppenheimer expansion, we Born-Oppenheimer expression of the total wave function, we always take the product of nuclear wave function and the electronic wave function. So we can consider a single electronic state. We are now blind to the other state. We are just seeing a single electronic state, and we can write down the total wave function as the product of nuclear and the electronic part. This way of representing total wave function is called Born-Oppenheimer adiabatic approximation. So this is called Born-Oppenheimer adiabatic approximation. In adiabatic approximation, we do not see any other configuration. We only look at a single electronic state that is represented by I, or in other words, if it is ground state, then if it is ground state. In this approximation, it is assumed that electronic states are well separated in energy, and total wave function can be expressed as the product of nuclear and electronic parts in a single electronic state. Under the adiabatic Born-Oppenheimer approximation, we stay blind to the other electronic state. We stay in a single electronic state, and this is why we preserve the electronic configuration. Preserving electronic configuration in molecular quantum mechanics refers to the adiabatic approximation. So when you say adiabatic approximation, it means that we are maintaining a particular electronic configuration. As I said, that this big ball is represented by sigma 2 pi 2 pi star 0 sigma star 0 configuration. So this configuration will be retained all the time for different nuclear configurations. But adiabatic Born-Oppenheimer approximation breaks down when if the electronic states are very close lying. Let's say we are not in this regime anymore. We are in this regime. Let's say we are not in this regime of the potential energy surface. We are in this regime where different electronic states are coming closer and they are very close lying. In that case, one cannot say that this electronic part can be represented by a single configuration. It should be addition of multiple configurations. So total electronic wave function cannot be represented by a single electronic state. Rather, total electronic wave function has to be represented by summation of different electronic states. It means that I will sum ground state electronic wave function plus then nuclear wave function of excited state multiplied by excited state electronic wave function plus all these summations we have to add. And this kind of expansion is called Born expansion, which leads to non-adiabatic wave function. Non-adiabatic because we are mixing different electronic configurations. So Born-Oppenheimer approximation breaks down if electronic states are very close lying. Then representing total wave function with the help of only one electronic configuration is not appropriate. Right approach is to take all important contributions. Above representation is called Born expansion of the total wave function. In this case, total wave function is no longer adiabatic, rather it is non-adiabatic because we are now mixing electronic configurations. Here, one important question is obvious. Do we need Born or Born-Oppenheimer expression of the total wave function to deal with photoexcited system? After a molecule undergoes vertical photoexcitation, the electronically excited molecule evolves its structure on the electronically excited state surface and very often encounters surface crossing region, the region where potential energy surfaces cross each other. So often potential energy surfaces looks like this in the whole multi-dimensional space. So when we photoexcite near the photoexcitation regime, near the Frank-Condon regime, the potential energy surfaces can be well separated, but the moment nuclei start moving, it may encounter a region where surfaces may cross each other. At the Frank-Condon geometry, electronic states may stay well separated, but as the electronically excited state species approaches surface crossing region, electronically excited states come closer. This is why if we want to explore the entire passage of a molecule from Fc point to the surface crossing region, we have to use Born expansion. So Born expansion is very important for the photoexcited system. Our next question is, how do we express psi? How do I express? So if we understand that this is the final total expression, the total wave expression for the total wave function, and that should include many excited states. Next question is, how do we express nuclear wave function as well as electronic wave functions? So if we know how to express it, then we'll be able to express total wave function. To represent electronic part, we clearly need a method which can represent both the ground and electronically excited states on equal footing. For an example, one can use complete active space self-consistent field method, CAS-SCF method, and by this method one can access electronically excited states. This method is not like single Slater determinant approach like MP2 or Hartree-Fock. In CAS-SCF method, one can access electronically excited states because we include the configurations, different configurations in the total electronic wave function. So we'll try to understand what does it mean by this CAS-SCF approach. Here, what we have drawn different configurations for electronic configurations. So these are the levels which are corresponding to the molecular orbitals, and we see that molecular orbitals are fully occupied below this level for the first configuration. So they are doubly occupied. So this represents one configuration. In the second configuration, what we have done, we have excited one electron from this to the upper orbital. We have double excitation, and then we have low-lying orbital excitation as well. So there are many other excitations one can include in this. What is unique in CAS-SCF method, we consider that a particular set of orbitals are chemically important, which is called active space. Electrons are allowed to shuffle in that active space only. So we'll not consider, once we define an active space which is chemically important molecular orbitals, we know that molecular orbitals are involved in chemical bonding, and we'll assume that okay, this particular set which is shown in this box are representing the active space. And if this is the active space, then none of the electrons from low-lying states from here to here, this kind of electronic excitation will not be allowed, or this kind of electronic excitation will not be allowed. These are not allowed. Only allowed electronic excitation or creating configurations, different configurations would be within this box only. So remaining electrons remain frozen or remain like not contributing to the electronic excitations. So this is all about CAS-SCF procedure. The hierarchy in the CAS-SCF method is following. In the CAS-SCF method, each electronic state is expressed by a linear combination of configuration state functions. Configuration state functions, each configuration corresponding to the configuration state function. So we take the linear combination of the configuration state functions. Each configuration state function is anti-symmetrized product of the molecular orbitals. So this is nothing but a product of molecular orbital, but particular kind of product where the antisymmetric nature of the electron has to be preserved. And that's why the product is called antisymmetrized product of the molecular orbital. These are actually expressed in the determinant form. This is called Slater determinant. So each configuration state function is a Slater determinant, and multiple configuration state functions we add and we get the final electronic wave function. In the single Slater determinant approach, for example MP2 or Hartree fork, in those methodology we do not use this expression. We only use a single configuration state function, and that's the only difference between CAS-SCF and other single Slater determinant approaches. And each molecular orbital is expressed as a linear combination of atomic orbitals. In computational chemistry, atomic orbitals are represented by basis set such as Popol's split valence double zeta basis set 631G, or Dunning's correlation consistent basis set like CCPV-DZ. There are many other basis sets which are available in computational chemistry. So with the help of this basis set, one can express molecular orbital. Taking the antisymmetric product of molecular orbital, we get the configuration state function. Each configuration state function will be added and to get the final electronic wave function. So this is the hierarchy which is used for the CAS-SCF methodology. We'll stop here and we'll continue this module in our next lecture.